Bioinformatics.
Welcome to the lab on read mapping. And so this is going to be one of several labs where we deal with read mapping and calling variants, etc. But this will be the first one. And in this one, we're going to look at two popular read mappers or aligners, BWA and Bowtie 2. The goal for this lab is to be able to take a reference, index it, and then take raw reads from a FASTQ sequence file and map them onto your indexed reference, which will form the basis of a lot of downstream analyses. Again, this lab follow along is not intended to be watched start to finish. This is meant to be a resource for you, so just feel free to skip along until parts that you actually want to see how I do things. So to start this lab off, let's go ahead, like always, and make a directory to be working in. So I'm going to call today's lab directory mapping, and I'll cd into mapping. Now, I like to stay organized. I don't like to dump all my files for all my different things into one directory. And so here, what I have you guys do is make a directory within mapping called refs, and within that make another directory called Ebola. Now, the reason I'm making all these kind of nested folders is because, as you'll see in a little bit, when you download references and then you index them, they can multiply in the number of files. If you index a reference, you can end up with 10 different files associated with it. So rather than get a bunch of clutter, I like to confine it to one directory. Notice I'm putting the -p here in front of the names of the directories I want to make. This is just an argument for make directories that it will actually build all the necessary folders to dig down to the directory you want. If you were to execute make dir ref/Ebola and there was no refs directory already there, it would kick back and say that it can't find that directory to make Ebola within. So, -p basically says, go ahead and make it if it doesn't exist already. So we're going to make directory, we're going to add -p, we're going to call it refs/Ebola. Okay, now if we ls, we can see refs, and we could ls refs and, we could ls refs and see that Ebola is in there as well. Now, let's go ahead and download a reference. And we're going to use a sequenced and assembled genome of Ebola, kind of continuing our theme that we've been working with. So this should be old hat to you at this point. eFetch, database, nucleotides, format FASTA. Here's the ID number we're going to download this time. It's an Ebola genome from 1976. And so we're going to redirect our output to the mapping directory, which we're actually already in. So you could cut off this first part if you wanted to make it just a relative path. Within the refs directory, the Ebola directory, and we're going to name it 1976.fa. Okay, so think to yourself where that is going to wind up, and then double check that it wound up there. So if I were to ls refs/Ebola, again, I'm using tab to kind of complete these things to make sure I got the pathing right. We hit enter, there it is, 1976.fa. So we're going to compare BWA and Bowtie 2. We'll start with BWA. We talked about this one in lab. This is a very popular mapping piece of software. So we're going to conda install bioconda as our repository, BWA, and we'll just by default say yes to whatever it asks us. Okay, now while that's installing, what we're going to do next is we're going to index that reference that we just download. Again, when I say reference, what I mean is an already assembled chunk of DNA or RNA or a whole genome, something that is basically contiguous or lots of large pieces that we want to take our small pieces and fit onto, find out where they fit on that, what we call a reference. So and again, you could look at the manual for BWA in your own time if you want, but to index, it's really simple. We just pass the index argument, and then we provide a path to a FASTA file, essentially. So BWA index. If you wanted to do this with Zika, we've got to reference Zika before in earlier labs, as well as raw reads. You could go and do this with Zika if you wanted to. So we will do this to I'll provide the absolute path if we want. Mapping refs, Ebola, and then tab that out to the 1976.fa and hit enter. And that was very quick. Again, Ebola is a very small genome. It's viral. If we were doing this with a human genome, even just one chromosome, it would take much longer. So let's look at what this actually made, because I mentioned that it can make extra files. The bigger the reference, the more files it tends to make. But let's go ahead and look at ref/Ebola with ls. And you can see that one file has now become 6 files. So this is why we wanted to confine these things. If you were mapping to multiple different things, all of a sudden you would end up with a directory that had many, many different files. So this is kind of the first lab that we've dove back into since we started just getting a little more proficient with Shell. And so why don't we start to apply some of those things that we've been practicing, thinking about something like an environmental variable. We're going to be referencing this indexed reference throughout the rest of the lab. And rather than every single time having to type /ref/Ebola/1976, why don't we do something a little bit shorter and easier and make an environmental variable called ref and set it equal to an absolute path to that. So this ref variable should work no matter where we're at. So we could say ref equals home directory /mapping/refs/Ebola/1976.fa. Now let's test, make sure it worked. Let's cat ref. So remember, put a $sign in front of it, and we just catted the whole thing. If we were in the home directory, we could still cat ref. It doesn't matter where we're at because we provided an absolute path or a full path. So we'll cd back into mapping. And now let's go ahead and use this thing. So regardless of whether you're watching this or not, don't take my word for it that your environmental variable is working. If you somehow put a typo in this path to the file, it will not work. And you will not get necessarily really informative errors when you try to run your read mapping. So make sure that you actually have the correct location of your file and your variable, otherwise it won't work. Always head your variables to make sure that they're actually working the way you think they are. So I would head that reference or cat it, whatever you want. Okay, and so just to show you that this is working, let's just rerun our index since it was nice and fast. And now to do our index, we could actually just execute it like so. Okay, same thing. Okay, so how do we now use BWA to actually map raw reads to this indexed reference? And so BWA uses an argument called mem. It used to have an argument called align, and it's actually still in the package. It's just this is a new, better algorithm. And so even though it's the same tool, things change over time. So we'll be using BWA mem for all the mapping. Well, if we're going to align raw reads, we need to get some raw reads first, right? So let's go ahead and map some 2014 Ebola strain raw sequence data to our 1976 reference. And so what I'm going to do is I'm going to, just like we've done before, put together a CSV table of a bunch of different SRA accessions from that project ID. So we've done this back when we were searching databases. So I'm going to kind of breeze through this. And if you recall, it sometimes can take a few minutes. This is a good time to point out a little tip. You don't have to wait for everything to finish. If you want to run a command while another command is running, you very much can do that. So you're probably familiar with using Control-C to stop a command that's been running too long. You can also put a command to sleep with Z, Control-Z, kind of like snooze, kind of something like that. And if you hit Control-Z while something is running, it will pause it. And then if you type BG, it will move it to the background. And so let me demonstrate. This is kind of a short running command, but I think it's long enough that I can show you. So this is running. I'm going to hit Control-Z. Notice it says it's stopped. It's really paused. Now if I hit BG, now it's running in the background. And so now I'm free to head the reference or do whatever else I want. And it'll eventually let me know when it's done. So see here, when I execute another command, it also said, hey, this command in the background is done. So that is one way to work a little smarter if you're starting to do kind of longer things, like while you're letting an SRA file download, for example, with FastQDump. Okay, so enough of that. Let's go ahead and get these raw data. So I want you to go through this run.info. I'll just head it. and pick out an SRA number that you might want to look at. Again, in accessing databases, I showed you some of the code for actually parsing out just the first column of all the SRA numbers if you want to do that. I've gone ahead and I've picked this one here, but you should feel free to explore and deviate from what I'm using exactly. So whichever one you pick, we're going to go ahead and FASTQ dump it. And see, here's an example where you could sleep it. So Control Z and then put it in the background. Now you could always type BG to see if it's still running. So if I type BG again, it says, hey, there's already a job in the background. I could type foreground and bring it back to the foreground again as well. So now it's running and I can't do anything else now other than put it back to sleep and background it again. So now that our file's finished downloading and we can see them here, as always, I like to head things just to make sure that they worked. Yep, that looks like a FASTQ format to me, 4 lines. Okay, so now that we have both of these files, let's go ahead and set them as environmental variables as well. That way we don't constantly have to be typing these long numbers and letters. So by convention, we'll put our forward read as 1. So we'll call this read1 is equal to, and again, we could just type it out right here and set it equal to the file name. But again, that will no longer be useful if we ever move out of our directory. So get in the habit of, if you're setting files as an environmental variable, to provide a full path to where they're located. So that'll be R1. R2 will be equal to the same thing, but _2, right? Okay. So again, I have my original directory named mapping. If you did something else, if you called it lab 8, something like that, you need to make sure that you put that there. Otherwise, these won't work, right? So to use BWA-mem, it's really as simple as providing in this order the reference, and then the forward and the reverse, or the read 1 and read 2, and then redirect it to an output file, which is going to be a SAM format, so we'll name it accordingly. So here we can say BWA-mem reference. Now in this case, I want to show you that BWA will throw some errors up that are worth looking at if you have issues with how your paired files are split. So rather than give it what it should get, which is read 1 and read 2, let's give it 2 copies of read 1 and see what it says. So BWA-mem ref read 1 and read 1, and we'll pipe that to bwa.sam. And so it's going to start. And notice it's starting to throw off a bunch of skips, and it's, in general, really not very happy. So let's take a look and see how our SAM file from doing it wrong looks after we see all these errors about skipping orientations and all sorts of stuff. So it still actually gave us an output, but this is why it's important to look and think about what's actually happening, because BWA went along, it gave us a bunch of really kind of poor maps because we gave it 2 copies of the same reads, but it tried to warn us while it was running. So it's important to kind of look at these things and not ignore things as they're running. I know you don't know what all these different things mean, but this is just kind of one of those things you just, as you use these tools, you start to see that, oh, I don't remember ever seeing that pop up before, kind of thing. All right, so let's run this the right way. BWA-mem ref R1 R2 to bwa.sam, and now it looks a little bit happier. So we'll let that run and then we'll come back. Let's move on to testing out Bowtie 2, another popular read mapping software. So we'll install this from Bioconda repository, Bowtie 2-y, and go ahead and hit enter. Now, once this is done running, we'll just execute Bowtie 2 by itself so we can see some of the options as well, which is very typical for these type of software. So Bowtie 2, and here we can see lots and lots of options. Formatting is a little different. Here we're seeing a lot of the arguments being dash dash and then actually written out rather than just dash in a single letter. And so here you can see some of these different options, like very fast, very sensitive, all sorts of good stuff. So let's go ahead and work on mapping with Bowtie 2. the process is going to be pretty similar. We still need to build a reference index. And so every mapping software has a slightly different way of indexing things, so they need to be indexed separately. So here, we're going to use bowtie-build to build an index. Now, Bowtie 2 wants you to give it an in file as well as an output name. And so I like to keep the input name and the output name the same, so we can just use our environmental variable for the reference as a stand-in for the output name as well. And that's totally fine. So we'll go Bowtie 2 build, and we will build the reference, and the reference will be the output. Okay, and again, small, so this was very fast. And we can ls into our reference/Ebola directory and look at what's in there now too. So we've got originally some of our, now we've got some of our Bowtie 2 indices here that end in BT2. And let's go ahead and use the basic functionality of Bowtie 2. So Bowtie 2, we will input the reference, and so we designate that with an X. And again, if you execute Bowtie 2 by itself and read through the directions, you can find all this information as well. Our forward reads are going to be R1. Our reverse reads, or read number 2, are going to be under R2. And then we'll call this one, just for consistency's sake, bowtie.sam, and we'll execute it. Notice it's a little less verbose when running relative to BWA, but at the end you actually get some really nice information. So when this is done, we'll look at that. Okay, so this is done running, and so you can go and get some information about how the actual alignment took place. And if you look at the very bottom, we can see that the overall alignment rate was just shy of 40%, so really not very good. Part of this is because we never cleaned the data beforehand, and so we could make this a lot better. Now, if we wanted to see similar stats for the BWA output, we'll have to install a separate tool because we need to actually skim through the SAM file to get some of that information, since BWA doesn't readily get it for us. So let's kind of compare these. So to do that, we're going to need SAM tools. So we'll go conda install bioconda SAM tools -y. And we can use SAM tools flagstat function, and we will do bwa.sam, and it will pop out some good information for us. So here we can see that roughly about half of our reads mapped. Most of those were maintained properly paired, but then we had a lot of orphan or singleton reads as well. And so this did slightly better than Bowtie 2, but neither really did all that well. So if we want to compare two different aligners, it doesn't make sense to use real data. Often when you want to compare or benchmark two different things, you want to simulate data from a known source of a known quality so that you're comparing apples to apples. And so to do this, let's go ahead and explore how to simulate some data. This might be something you end up using for your project down the road. So to start, let's stay organized. Let's make a directory specifically for our simulation from our reference, and we'll cd into our refsim directory. Now, we're just going to pull down another Ebola genome, and we'll go ahead and save that in here. And we will set this as our new reference. So this will be within mapping, refsim, and there it is. Now, we're going to go ahead and index this just like we did before. We're not going to change our reference. We're not simulating a new reference. We're going to simulate raw reads being generated from it. So if we had went and extracted DNA from this organism and sequenced it a bunch of times, but if we knew every single possible error that could happen. So let's index this in both ways just to get it out of the way. So we'll BWA index this, and then we'll Bowtie. There we go. Okay, and so both are built for their indexes now. So we're going to use DWGSim to simulate 100,000 reads from these genomes. And at first we'll do it with a 1% error rate. And so this is a really cool tool that I encourage you to look at if you're thinking about trying to find data for your project. So let's conda install -c bioconda DWGSim. Now that this is running, let's go ahead and do our DWG sim and execute it so that we can see what kind of options are in here. Now, I'm going to be using the big E and the little e option. And so if you were curious what those are, these are basically the error rates of your first and second read, because we're going to have this simulated as paired read data. Okay? And so you can also simulate different sizes, the lengths of the read. By default, it's going to be 70. You can simulate the insert size between them and so forth. So here the outer distance of the fragment is going to be 500 base pairs. So you could subtract 70 from each side to get the insert distance. So we'll just use kind of the default settings for now. DWG sim -n, we want 100,000 reads, and we want the forward read to have a 0.01 error rate, which is pretty good, and the second read to have 0.01 as well. And we will build it from reference, and we will just call this data as our output name. So let's look. So now we've got some nice information that shows us where the actual mutations, the errors, are. This is data you wouldn't have if you had real data, because you don't know going into it where the mutations are. You would have to try and figure those out with algorithms. So here are our forward and our 1 and 2 reads right here that we can use. And so those are what we're going to be using as our stand-in for real data. So let's go ahead and set those as read 1 and read 2. Now, I got lazy here and I didn't put the full path. I'm just going to say, you know, we probably should have done that. If we don't leave the directory, it doesn't actually matter right now, but I'm trying to teach you better practices, so I'll fix that before you guys actually see this thing. So refsim, and we'll call this one data.bwa read1.fastq, and this one will be the read2, and make sure that you change the R1 here to an R2. I have done that on accident and not done that. Now, let's go ahead and rerun some of our alignments with this known data set. To compare, I'm also curious how fast and efficient these things are too. So if we put time before any command, we'll actually get an output of how long that command ran, so you don't have to sit there with a stopwatch. So we'll go time, bwa mem, ref, R1, R2, and we'll pass this to bwa and we'll call it sim.sam, and we'll hit enter. Now this should be faster because this is fewer reads. You know, this is only 100,000 versus almost 1 million. And so this took just shy of 4 seconds or so. And let's look at how the quality was with SAM tools. So we're going to use that SAM tools flag stat on BWA sim. And we can see that we had about 95% were properly aligned and paired. So that's really great. Let's try it with Bowtie 2 now. So we'll time Bowtie 2 -x the reference -1 R1 -2 R2. Pass this to Bowtie sim.sam and execute. Taking a little bit longer. I also know that because I wrote down what it took in the lab, but it should take around 10 or so seconds. Again, this will vary a little bit. So it took around 13 seconds, so pretty close. And we ended up getting a 94% overall alignment rate this time, which is pretty good. And so they both did pretty similar as far as their ability to align, although Bowtie took longer to do it. Let's go ahead and overwrite our data with data that are a little bit more error prone. So here we're going to have an error rate of 0.1. So an order of magnitude more full of errors. And let's see how these things do with even more, you know, with dirty data. And so because we're using these environmental variables for R1 and R2, and if you type ls, you'll see that the data actually just got overwritten because we still named it data. We can still use our environmental variables. So we don't have to go and retype everything. We can just hit up and take a peek at things. Okay, and so now we're having issues with pairing because the errors are throwing up issues. So here this took about twice as long. Now let's SAM tools, so SAM tools flag stat the BWA sim, and take a peek at this. So now it's doing okay, but not nearly as well as it did before. It's got some more singletons. and went from about 90% to 80% as far as mapping rate. And again, you should be getting 100% mapping rate because all of these reads, there's no contamination. We know that these came directly from the reference. There's just some mutations or errors in there. And so let's try this with Bowtie 2 this time. And when this is done, I'll SAM tools this one as well so that you can see something comparable. So Bowtie 2 took about the same amount of time as it did the first time. So let's go ahead and do Bowtie sim.sam. And so here we're actually seeing a much lower rate of mapping relative to how the BWA performed. So what I got when I originally ran this was around 83%. So just now it was about 81, so kind of same ballpark in about 6 seconds. And now we're down to around 28%. Here I'm getting 29% of overall mapping rate. So this time Bowtie 2 was faster, but it was faster and did much worse. So maybe what we need to do is tell Bowtie 2 to take a little more time and be more sensitive. So we could use the very sensitive local argument, which is the kind of way of spending a little more computational power to try and do a better job. And so we'll let that run. It's going to take a little bit longer. And if we go ahead and SAM tool it, we'll see that we're getting around 45 or so of these things mapped, 45%. So it's gone up, but let's just kind of go crazy. And I don't expect you to know what all these settings are, but let's just say you knew the perfect settings. You knew, if I set this setting for this and that, how perfect could I get the read mapping? Now, you would never know what's considered right or wrong with real data, but let's see what Bowtie can do under ideal circumstances. And so now we're up to almost 80%. So with all this kind of fiddling around, we were able to get it performing just about as well as BWA. So can Bowtie 2 do as well as BWA? Absolutely. Can it do as well just with default settings when you don't know everything about your data? No. BWA tends to be a bit more robust. And so if I was just in the dark about my data and I wanted to do some read mapping, I would probably use BWA. So I know that this is, kind of just pushing a bunch of buttons right now. So I wanted to take a minute and show you kind of what this actually looks like. So hopefully you took the time to go and download Tablet. This is a really kind of lightweight way of visualizing alignments. And so I already have that installed. And what you're going to want to do is download both your reference files as well as your SAM files. So when you have those, you'll be able to map them back on top in Tablet. And I'll show you how to do that. So here we are in Tablet. I'm going to go open assembly. And once you've downloaded these things, you'll download, in this case, I downloaded bwasim.sam. And then I also downloaded the reference that those reads were generated from. And if we hit open, it'll think for just a second. And then we'll have this little box over here that we can click on. And now we can see all of our, and again, this is only 100,000 reads. So here is kind of the whole overview of the length of the reference, and this is our viewing window currently. So we could actually kind of look more towards the tip, and we can see all the different reads that were aligned against this. And we can play around with the read color. We could look at like the nucleotide sequence if we wanted to. We could do all sorts of stuff to kind of play around with this. We could look at directionality of the reads. And so I would encourage you just to kind of take a second and kind of explore. You could even see where all the variants are. In other words, where are all the errors? And these are all lit up. You can see this is, again, very, very full of errors. So maybe also try visualizing the Ebola stuff that was real data as well and see how it compares. So that was the lab for today. We're actually going to be doing a lot more with read mapping in the next lab. We're going to be looking at how to actually call regions where there's a consistent variant in the individual that you sequenced relative to the reference. In other words, where has there been actual polymorphism and all sorts of fun stuff.